All right, so in that last video, we began chatting about this idea of using these Hamming 7-4 codes to actually take some nice little message and begin adding some of these redundancies. The idea here is that I could start with whatever your favorite 4-bit message happens to be. So let's say it's a 1100. And what I want to do is I want to encode this thing into a 7-bit code word. The way that we did this was to construct the code word by taking X and multiplying it by this matrix G, using this crazy twisty multiplication. And what's going to emerge on the back end is that I'm going to get my original message, the 1100, paired with its 3 extra redundancies. So the 100 at the end. The hope then is that I can push this little code word through some unreliable or noisy channel. And then if any of those bits actually flip, I'm going to be able to easily detect and then if necessary, correct any possible error. So now we want to begin chatting about how we're actually going to go about this idea of detection and correction. And what's cool about it is that it's all done one and the same, is that it's all one simple operation that's going to scream at me if there's an error. And when it screams at me with an error, it's actually going to tell me where that error occurs. And the way that it's going to go about is actually going to come from that cool little structure of that matrix G. So earlier I alluded to the first part of that was this nice little identity matrix. And now that second part of it is going to have those 4 little rows, each of them of length 3. So we have the 111, 011, 101, 110. So at that time, I'd mentioned basically that that section was constructed by taking all of these little 3-bit strings and only including those that have at least 2 ones in them. So what I'm going to do now is I'm going to begin creating a new matrix that also has those things that only have a singleton 1 in them. So I'm going to create this little H transpose, which is this matrix down below, drawn in red. It has the same top 3 rows, so 111, 011, 101, 110. And now I'm going to stuff in the 100, 010, and 001. What you can see is that this thing is in fact going to have 7 rows, which is exactly the same length as my code word. So those two things are going to play very, very nicely with one another. There's a little bit more going on behind the scenes, actually. You maybe can already see it a little bit, in that 7 is often viewed as 8 minus 1. And if you look at those rows of this H transpose, you can see that if you were to represent those binaries into just regular decimal land, you would see that those rows actually correspond to the numbers 1 through 7. You have a 7 up on the top, all the way down to the number 1 on the bottom. I've organized them in kind of a weird, chaotic way, but it's exactly that. And when we come to actually designing this thing, that's exactly what we're going to do, is we're basically going to cycle through numbers, write them in binary, and then organize them somewhat cleverly in this H transpose. The thing it's missing then is obviously the 0, which I can view as just triple zeros, and that would maybe go on the bottom here, but I'm not going to include that along the bottom. So that's all H transpose is. And what's cool about this is that it's set up in this very clever way that it's going to allow me to easily identify any error that you would make on that actual code word. So it's this fun version of being a magician, basically, is that I'm stacking the deck in my favor so that if you change any of those little things, I'm automatically going to know that you've made an error or you've changed something, and I automatically know where that change is going to occur. So it is a fun little bit of magic, and it really just comes from moving around numbers 1 through 7 in a somewhat clever way. So the way that we're going to do this is by constructing what's referred to as the syndrome. So the syndrome is going to be computed by taking whatever code word we receive. So let's say we receive some C, and I'm going to now multiply it by this H transpose. The hope then is that this is just going to kick out triple zeros. If it kicks out triple zeros, then life is great and I don't have any errors. If it kicks anything else other than triple zeros, that's actually going to signify that an error has occurred. And then we're going to have to start round 2 of actually finding out where the error was and then begin fixing things. So formally, this matrix is referred to as an H transpose. You could technically just record this as an H because we're never going to use the other version of it. But this notion of transpose is going to come into play a little bit more as we go further. So transpose are basically where we take the rows and columns and then we swap them. So if you think about this original matrix Q, we had this top row of 1, 1, 1. Well, its transpose would then have the first column of 1, 1, 1. In the next thing, you'd see that I have a second row of 0, 1, 1, which then means I have a column of 0, 1, 1. So H transpose technically comes from taking the transpose of this little matrix A, but we won't actually need this one. But it is kind of a cute way to see all of these numbers from 1 to 7 written in binary. And that's exactly how you want to be thinking about this thing, is that it's keeping track of all of those things. It's also going to be part of the reason why there's a 7 in here. That thing is always going to be of the form 2 to something minus 1. So when we allow for codes of like 5 or 6 or something like that, we're going to be changing that first number into some power of 2 minus a 1, so we can run this same little structure over and over and over again. Okay, so let's play around with this syndrome just to see what's going to happen. So if I have no error, what I'm hoping is that when I multiply my little code word by this H transpose, it should in fact kick out triple zeros, signifying that there's no error. So that's exactly what I'm going to do. I'm going to take my little code word of 1100100. I'm going to place that over here. Try not to move everything. And then I'm going to do this twisty multiplication by taking that little matrix and multiplying it by this bigger matrix. I've tried to keep things somewhat organized down on the bottom. So I'm going to view this first column as the orange one. The second column is then this red one. And then the third one is going to be this green one. And then when we do the twisty multiplication, we're just going to match things up. So if I match them, I'm going to multiply them and then ultimately add those 7 little things together. So that first row in column, so the blue row and the orange column, you can see that I'm going to get a 1 and a 1, which is that. Then I'm going to get a 1 and a 0, which is that 0. Then I'm going to get a 0, and I don't really care, which is going to give me that 0. Then I'm going to get a 0 and a 1, which is going to give me a 0. Then I'm going to get a 1 and a 1, which is going to give me that 1. 0 and 0 is obviously going to give me a 0, and 0 and 0 is going to give me a 0. So if I take those 7 things and add them all together, well, 2 of them are 1s and everything else are going to be 0s. You can see that it adds up to a 2. But if I'm doing all of this thing at the bit level or at mod 2 structure, that's going to reduce down into a 0. Same thing then for that second entry. I'm going to now take all of those blue things and pair them with the red things. So the 1 and 1 makes a 1. The other 1 and 1 is going to make a 1. The 0 and 0 makes a 0. The 0 and 1 is going to make a 0. The 1 and 0 is going to make a 0. The 0 and 1, which is coming from those two, is going to make a 0. And then the last 0 and 0 is going to make a 0. Adding all of those things up is obviously going to kick out a 2, which is then again going to reduce down into a 0. And then same thing for the very last one. You can see the interesting ones are going to come from 1 and 1, which makes a 1. 1 and 1, which makes a 1. That one's going to be 0. So 0 and 1, which makes a 0. 0 and 0 makes a 0. 1 and 0 makes a 0. 0 and 0 makes a 0. And 0 and 1 makes a 0. So we get 2 contributions early on. That whole thing then adds up to a 2, which reduces down into a 0, which is going to give me that. So this is referred to as the syndrome. So you're going to take your original code word, multiply it by this crazy matrix HT. And if that kicks out triple zeros, we know that there are no errors. So nothing has actually happened in transmission. So that's going to be the good scenario, is that I push this thing through this possibly noisy channel, but the channel was not so noisy that it actually gunked things up. So no problems. We just keep on marching along afterwards. I'm probably going to pause it here to then switch it into the scenario of what happens if we do have an error. And that's where we're really going to see kind of the fun magic emerge, and that it's going to be this cool way to identify, hey, an error has occurred and I know exactly where it is. And it's a lot of fun. So stay tuned. It's going to be the same little bit of twisty multiplication, and then we'll pull up some Python to actually do this, not by hand anymore,